Well, hello, welcome back. We are now in Chapter 8 of the very heavy chemistry part of this class. It'll get more general science coming up. Well, not next is organic chemistry, but we're getting closer to general science. So still heavily in chemistry, oxidation and reduction. Here are the learning objectives. And start off with oxidation. Well, kind of what it is. So fire, if you're wondering what fire is defined as a rapid oxidation reduction reaction. And here is ammonium dichromate forming chromium 3 oxide, nitrogen gas, and 4 waters. Which you can't really see in this picture. Chromium 3 oxide is it's a forest green kind of color. It's like a pineish green color. I don't really like, well, when you see it in real life. Um, Kind of smells like eggs to me. That's just my own perception. But well, I've never seen ammonium dichromate in person, but certainly chromium 3 oxide. They put that in some of the pigments, like if you go to the to Shangri-La in Honolulu and with the art museum, there's some various pigments that they have there that are kind of old, and the forest green one is chromium 3 oxide. Okay, so definition of oxidation reduction. So oxidation, so gain of electrons, and reduction is then the opposite, is losing an oxygen. So this is why they go together. Whenever something gains oxygen, something's going to lose oxygen. Makes sense. Oxidation is losing hydrogen, reduction is gaining hydrogen. So this is more of a placer in organic chemistry. So if hydrogen is added to something, that is considered reduction, and if it's losing, it's considered oxidation. Why is that? Because hydrogen is electron rich. So there's a various high level electron density in hydrogen, and that it adds density to the molecule. So that's why it's considered oxidation reduction there. This is the most general here. Oxidation means losing electrons, and reduction means gain of electrons. So this is the best definition here. It's the same as the bottom one. Losing electrons is also the increase in the oxidation number. The higher the oxidation number, the more positive the atom is, or ion. And then reduction being the gain of electrons, and a decrease in oxidation number. A negative oxidation number means more electron density. And with the oxidation numbers, this is different than when we were talking about quantum mechanics, and I'm even using the words electron density. That's of course the most proper way to say it. The electrons are not dots; they're kind of fuzzy clouds. So if you're used to the Lewis structure, the idea with oxidation numbers is that one of the atoms owns the electrons, or it does not own, so it makes it easier for bookkeeping. Okay, and if you can't remember the previous slide, think of Leo Gur. Leo is like lion, Leo's roar, Leo Gur. Leo, loss of electrons is oxidation, Gur, gain of electrons is reduction. Whatever works. I don't like mnemonics, but if that works for you. So to give you an illustration, we have this is burning of methane and oxygen. So carbon, and you can see here, you're literally adding oxygen. So adding two O2s. You're adding the plus two O2s. You're adding oxygen. This is an oxidation. The methane is being oxidized, and the oxygen is being reduced. And in this case, both the carbon and the hydrogen are they are being oxidized. Well, I guess hydrogen, uh, it's already got a +1 oxidation state, but the carbon is going from an oxidation state of -4 to +4, so it's losing lots of electrons in this one. Okay. Oxidizing reducing agents. So oxidizing agents cause oxidation, reducing agents cause reduction. So let me return to the previous slide. And let me explain this. So we know that methane is being oxidized and oxygen is being reduced. So oxygen here so it's kind of the opposite. Oxygen is the oxidizing agent. It's causing oxidation. So causing oxidation, how does one cause oxidation? So oxidation means ripping electrons off of something, and in the process of ripping off electrons, that species becomes reduced. So the oxidizing agent, the delivery of oxidation causes that species to be reduced. Likewise, the reducing agent delivers reduction. How do you deliver reduction? You deliver electrons. And in delivering electrons, you are reduced. I'm sorry, oxidized. Blah. Delivering of electrons means oxidation. So the reducing agent is oxidized. And also with this, the most common reducing agents that we have are fuels. So are the most common reducing agents. We also call certain reducing agents in our body antioxidants. So if you wonder what antioxidants are, they're reducing agents. And the most common oxidizing agent, is oxygen. Not surprisingly, it's 1/5 of the air. Okay, so we've already covered that. And here's an application of oxidation reduction, the photochromic glass. So I don't have these glasses. I've thought about buying them. They're kind of cool, but in the presence, it says sunlight, but it's really ultraviolet light. In the presence of ultraviolet light, an electron is produced, and they usually put silver iodide in there, and the ultraviolet light hits off the electron from the iodide and makes silver metal, and that's what darkens the glasses. So I believe they're called transition lenses. They're clear in the inside and they turn dark on the outside. Look kind of cool, but I don't really need glasses, so but I do need sunglasses because of my blue eyes. But anyways, it's kind of cool. Maybe if I win the lottery, I'll buy some of these or something. Okay, and another application of oxidation reduction is actually batteries. So we'll talk about this in a second. But here, if you stick copper into silver nitrate, so here it doesn't say silver nitrate, but that's one of the few things that silver is you can dissolve in. So you have the silver ions there, and they will be reduced by the copper metal. The copper metal is oxidized, and the silver ions are reduced, and you get the silver growing on the copper there. This is a fun experiment to do. And you can see the solution turns blue. So the solution marked B, if you can't see it, it's got a light blue tint. And I like playing with copper because I like those blue colors. So that's one cool thing about copper. It's very, very pretty to play with. This is also one of the ways you can, if you get a noble metal nitrate, you use like gold nitrate, you can stick jewelry in it and you can coat it really quickly. This is the electroplating kits at home. But warning, if you use these stuff, they're don't get them in your eyes. And also, if you do the silver nitrate, that will turn your skin brown. At least for me, because I'm very Caucasian and white. So the lighter skinned people, the silver nitrate will definitely noticeably turn your skin brown. At least I only know this from personal experience. I don't know about people that have naturally more melanin in their skin. So, all right. And application of oxidation reduction are batteries. So anodes and cathodes. So the cathode is the source of positive charge. So remember that the T means plus. So cathode is the plus charge, and anode is the negative charge. One of the ways I remember it is the anode corrodes. The anode corrodes, and the corrosion is from oxidation. So if you want to do mnemonic devices, anodes corrode, cathodes grow, and the plus sign, the T. The negative charge from the anode goes towards the cathode, the positive charge, and then the anode corrodes because what happens in negative? Well, a metal loses its electrons and becomes an ion and goes into solution, so it corrodes. And then the cathode gains an electron, and it it the metals in solution will form around it. It'll grow. And if if you're working with batteries, be careful for the positive one. The cathode, the positive end, that's the end that sparks. So if you're ever working on batteries, that's the sparky end is the cathode. Okay, so we mentioned this silver before, the copper and the silver. Here's what's going on, and it is a battery. You could use this as a battery if you wanted. So copper metal goes to copper plus 2 ions. That's the blue color in solution and generates 2 electrons. Silver absorbs an electron to form silver metal. And in this case, we actually need to have 2 silver. So here's the balanced chemical equation here. And if it may look confusing because you're like, well, why do we have why can't I just get rid of the silvers on both sides and put copper plus silver makes copper plus silver? Why do I have copper plus 2 silvers? It's because of the electrons. So because the oxidation is generating 2 electrons and the reduction is only absorbing 1 electron, so that way you have to double it to get that. So here's where the battery would be, and you have the anode is the copper, so the anode corrodes, so the anode's going to go away, and then you have the silver as the cathode, and in the experiment thrown into the test tube, you just threw it in there. In this case, we have a wire that connects the anode and the cathode. And now as the electrons flow, we can have it do work. Here it hooks up to a light bulb, but I mean you could do whatever you want to have it do. If you want to have it run your cell phone, if you want to have it run a remote control car, whatever, run a flashlight like here, whatever you want to use the electricity for. And so one more important thing for this battery, you need to have a salt bridge. You need to have a way that the ions flow. So if you don't have a salt bridge, and that's the porous partition there. If you don't have a way for ions to flow, you would, in order for the battery to work, you would have the negative charges going on the flowing towards the silver, and then the positive charges gaining on the copper. That would not just randomly happen. So you would have a buildup of charge, and that's not energy favorable. So there has to be a way for negative ions to flow towards the anode and positive ions to flow towards the cathode. And that's what the porous partition would do there. Another way you can do it, as I said, is a salt bridge. If you make this in the lab, usually what we do is take either it's a couple ways you can do it. You can like soak pieces of paper in a salt, like potassium nitrate is used very commonly, or you can have like make like a gel of something and have like a U thing apparatus, and then soak cotton balls and potassium nitrate or something, or potassium chloride, and stick those on the end. There's a couple ways you can do this, and okay, so and one thing about these batteries, the electromotive force, the EMF, is set by the metals. So if you think, oh, I'll make a better battery, how to make a bigger battery, I'll put a huge block of copper in there, and I'll have a standing pool-sized battery kit, and then I'll make this thing huge, and I'll have a huge potential is voltage, and if you connect it up, it's going to have the same potential as if you had just two atoms, a copper and a silver atom. I mean, it's the electromotive force is not proportional to the amount of things. So how do you get bigger voltages? Well, you have things in series. We'll talk about it a little bit more when we get to, well, I guess lead acid batteries are coming up soon. Okay, so other types of battery. Here is a dry cell battery. We tend not to use dry cells as much anymore. We tend to use more alkaline batteries, so the batteries you buy at the store tend to be alkaline batteries. Similar except the paste has potassium hydroxide in it as well. And um, the the battery. So when a battery dies, of course, when you run a battery, eventually the battery dies. How does it die? A couple ways can happen. The anode can corrode away to nothing, or the ions that are in it to form the cathode will be depleted. For most batteries that we have, the alkaline batteries, it's the zinc. So the zinc on the inside corrodes away, and uh, so here in this battery you have the cathode is, and when looking at this picture here, that the graphite rod in the middle, that's the cathode, and it's make sure it's not electrically touching the anode, because if so, the battery will just discharge and you'll get a dead battery by the time you have to go and use it. Uh, I remember in my youth, I took a hacksaw and I sawed a battery in half. That was kind of fun. If you want to do it, just of course, wear eye protection if you want to do it, and if you it looks similar to this picture. I mean, so the graphite rod is black, of course, and then the zinc casing. It's kind of a spongy looking thing, and then there's a gel in the inside, and that's the moist paste. But then it was an alkaline battery, so it's, of course, an alkaline. So be careful for your hands, and like I said, your eyes if you do this at home. Okay, and the cars have lead storage, has a lead acid battery. So this is a car battery, and the anode is lead and the cathode is lead oxide. So I've never taken apart a lead acid battery, and so a lead acid battery, it's the anode is lead metal, and then that's what these, and they're heavy. I mean, if you ever picked up a car battery, it's heavy. It's because it's made of lead, or there's a significant amount of lead in there. So that's why they're so heavy. And the anode is kind of a dull gray color. It's the lead, and the cathode is a lead oxide. It's white. So if you were to take it apart, that's what it would look like. And the uh, the anode turns into, well, both the anode and the cathode turn into lead sulfate, which is aqueous. You can see they use H2SO4. That's sulfuric acid. And then the why do we use lead batteries? Well, because they're rechargeable, and you can go them the other way, and then the anode and cathode can regrow on the battery. One of the things you can see here, that this shows like this squiggly line. That means that you have a level in them. Uh, Batteries, if the lead acid batteries, if you don't have if the liquid level drops, then the battery won't work as well. So if you ever wonder with batteries, sometimes they ask you, have you put water in your battery? Like, why would I put water in my battery? It's because of that liquid level there. And be careful for that liquid level. It's that stuff it's usually about 1/3 on the order of like 6 molar sulfuric acid. So be very careful with that stuff. So lead acid battery is actually very dangerous. The other thing is, if you're jump starting your car and you connect the the terminals incorrectly, you can have one of the lead batteries explode. So I mean, whenever I work with lead acid batteries, I'm always wearing safety glasses because of the fact that they could explode, and that sulfuric acid will blind you very quickly. So it also could disfigure you, but like at least you'll have your eyes to see with. So again, please be cautious. Okay, so other types of batteries, nickel cadmium batteries. We tend not to use these as much. We tend to use more lithium ion batteries. Lithium ion, these batteries, they move lithium ions between the anode and the cathode, the and you've probably noticed that lithium ion batteries tend to become less effective as time goes on. So the reason why lithium-ion batteries become less effective is because of overcharging. So it's actually the lithium ion. And if you put the potential, the voltage to recharge it, and if you put it on, if it gets past the full charge, the lithium ions will start to reduce to form lithium metal. And then that lithium metal will react with the battery. And the lithium metal damages the internal components of the battery. And that's why it becomes, specifically the interstitial fluid is usually what it is. That's the reason why lithium ion batteries uh, do not last long. So for me, when I'm recharging my cell phone, or computer or iPad and stuff like this, I try never to let it get to 100%. So, I mean, of course, like if you're leaving it in charge for a while, try if you can try to unplug it like in the 90 percentage ranges. And if you do that for a long, if you never let it charge to 100%, your lithium ion battery will last much longer than if you continually, like, the worst thing to do is to keep it at 100%. It's like, oh, I'm down to 95. Oh, time to plug it, charge it back up. You're just destroying the battery. So be careful with that. Fuel cells, these are interesting. One of the things, so like when you burn gasoline in your car engine, your fuel, your the efficiency, the amount of work you get versus heat is about 20%. If you use a fuel cell, you triple that. You get about 60% ish amounts of work versus heat. And the we're trying to get the technology. We can do it in small amounts, but we can't do it in big. Like a breathalyzer, for instance, is a fuel cell, or at least the more expensive breathalyzers, the one that the police use. I've never been breathalyzed, so I don't know what that experience is like. The NASA uses fuel cells. They use it in the Apollo space program and in the space shuttle. That's besides a battery. The primary energy was a fuel cell, and that's also, it doubled in that because the fuel cell is a hydrogen fuel cell, and that generated water for the astronauts to drink. So if you want a dangerous job, be an astronaut. Sit on a bomb, also known as a rocket, to shoot you off into space at 3 Gs, and then have to wait for a while to drink and eat something because the fuel cell is generating your water that you're going to use to drink. So, but I'd still like to be an astronaut. It sounds pretty freaking cool, to be honest with you. All right, so we talked about useful things about oxidation and reduction. Let's talk about bad things. Here's rust. So corrosion is a electrochemical process. So iron corroding to form. So rust is typically iron 3 hydroxide. So, or Fe2O3. That's kind of, well, that's like hematite, or iron 3 hydroxide. And the iron metal, if you notice here, usually you have a water droplet. So the anode corrodes, the iron is the metal that's corroding, and then the rust itself is the cathode. The cathode grows, and in that water you have an ion. That's where the ions flow. So one of the ways to get rid of corrosion is to make sure it's never wet. So the surface of iron will still rust with just oxygen in the air, but to if you probably know, if iron gets wet, it will start to rust more, and one of the ways to make sure it doesn't rust is to keep it dry. Another way to do it, you can paint it. So you put a coating over it, so, well, and to make sure water never gets there. Another way, you can put what's called a sacrificial anode. That's zinc is used very commonly. So galvanized steel. That's zinc. The zinc will be oxidized first. There's another process called pacification, and that's how aluminum works. So aluminum is considerably more reactive than iron, but so aluminum though creates an oxide surface, and this is called pacification. And the aluminum oxide is really, really tough. The common name for aluminum oxide is sapphire. So if you look at aluminum, I'm recording this on my MacBook right now, and it's the casing, and this is aluminum, and I'm looking at it right now. It has this white pattern on it. I am looking at sapphire. Sapphire is aluminum oxide. It's the second uh, toughest mineral on the Mohs hardness scale. Diamond being the hardest, of course, but sapphire or carborundum is number two for hardness. So sapphire is really, really tough, and it pacificates the aluminum. Aluminum's not the only metal that does this. Titanium does a similar process. Titanium is not as reactive as aluminum, but it's pretty reactive. And titanium oxide is very, very tough. So problem though with aluminum oxide, so for sapphire, uh, the chloride anion can penetrate through the pacivated surface. So you don't see too many aluminum boats in the ocean. You also don't see too many aluminum pipe fittings. And the reason is because of chlorine, so the chloride. And um, similarly for titanium, methanol will cause corrosion for that very quickly. Well, it takes a while for aluminum oxide to corrode in chloride. It's not as fast as titanium, but if you want to do this at home, you take some aluminum foil and you can put in some salt in the water and just let it sit, and the aluminum will corrode. You'll see like white flaky stuff coming out. What you're doing? You're making sapphires. So if you want to grow your own sapphire, that's why you can do it at home. Of course, I mean this is amorphous sapphire, so it's not very valuable versus the crystalline sapphire that that people use for jewelry. But sapphire they use those for like class rings, like when you get the class ring and you have the jewel on the class ring. It's those are usually sapphire. It's easy to grow sapphire in the lab. So, but anyways, aluminum pacification. And what about silver? Um, Silver tarnish is actually from silver sulfide. So using the sulfur that's in the air leaves a film of silver sulfide, and it's a black color. And if you see here the tarnish, you can get rid of it. Of course, what you're doing is you're losing silver, and silver is expensive. So one of the ways you can get this is to use reduction. Use reduction, and then the reduction with the bicarbonate and aluminum. So that will reduce the silver, and you can keep the silver. And so I'm looking at this picture, and they must have not dipped that in there very long, because if you see the black pattern on the edge of the bowl there, that's silver sulfide. So that's the decorative. So they can use it for decorative stuff too. Okay, so an explosion. I told you fire is a rapid oxidation reduction reaction. That's the definition of fire. And chemical explosions here, it's a fire. It's the basis for most of our weapons, with the exception being nuclear. And I guess they have some weapons that they use kinetic energy, where they shoot uh, using just, I guess the Navy has this. They have the guns that just shoot a projectile with a huge amount of kinetic energy. But here's one. It's a very common explosive using ammonium nitrate and fuel oil. Because this is really cheap, ammonium nitrate is a fertilizer, and fuel oil is just like diesel fuel. And um, this is the bomb that was used to blow up the uh, the federal building in Oklahoma City. So using this one, this is a uh, and this is a hard explosive to track too. I mean, it's pretty easy to track certain chemicals, but ammonium nitrate, this is harder to track, because we use it as a fertilizer, so it's a very commonly used thing. So, but here's the explosive, one of the more common explosives. We tend not to use this in the military for bombs and whatnot. Tends to be more for construction kind of thing, the explosives, and to like blow out a basement or blow out the side of hills, so you don't have to dig through them. So I already mentioned this for oxidizing agents. Oxygen is the most common, and this is by far, and this is because it's in the air. So when we use our cars, we drive around, the gasoline or diesel fuel is the reducing agent, and oxygen is the oxidizing agent. We don't even think about, gee, I wonder if the oxygen is going to be depleted in the air. We just wonder, oh, I wonder when my car is going to run out of gas. And then here's another one, ozone. Ozone is great in the stratosphere, so up high. Ozone is bad in the troposphere because it's corrosive. It's an oxidizer, and it smells pretty bad too. I don't like the way it smells. You can get this. You can kind of smell it sometimes around electronic discharge, like around power lines. You can smell the ozone. So other common oxidizing agents, peroxide. You can use this to bleach hair, and it'll lighten your hair there. And disinfectant. Well, one thing with hydrogen peroxide, it'll dissolve scabs. So you like if you have a cut and you want it cleaned out. One thing of it, it's nice to clean out wounds though, is because it'll get rid of the scabs and you can get rid of anything that's underneath them. And potassium dichromate. So we use this in breathalyzers. Potassium dichromate is a very, like if you know Despicable Me, it's this minion yellow color. So it's a really, really bright yellow. I told you the green is a forest green. It's like the pine tree color green. So and benzoyl peroxide, yeah, is acne treatment. So chlorine, yeah, we can use this to bubble it through water to kill things. Bleaches, so of course you can use bleaches in water. Um, it's typically what they do in swimming pools as well. But these are oxidizing agents. Usually you use calcium hypochlorite. It's usually sodium hypochlorite for the bleach. I use bleach a lot in my laundry. So, okay, so reducing agents. I told you the most common reducing agent is fuel. Carbon, and this type of special form of carbon called coke, is and used in reduction of metals. This is how the vast majority of metals are made, is by using reduction with carbon. So that's how we make a lot of iron, and steel. So you take iron ore and crack it with carbon. So ore reduction with carbon is the most common by far way to produce metals. And aluminum, though, aluminum is made with electricity. We make that with bauxite and cryolite. Those are the two ores of aluminum, and you hit that with electricity and carbon rods, and you form aluminum that way. Aluminum is not made by cracking it by reduction with carbon. Of course, it reduces. We use electricity for that, and but aluminum can be used to make chromium, and also good old school photography. So this is like if you imagine like the American Civil War or something like that, when they have the big flash, and you have the plate, like we have the glass plate to make the the picture. This works by the fact that the light causes it reacts with the hydroquinone and the silver ions. So it's the silver bromide. The silver is reduced. So and the quinone does that, and then you have the negative here. So then you have it forms a negative image on the plate, or in the old school, I'm thinking like Civil War era, or the film. Then you have there. Okay. And I told you in a previous lecture, antioxidants are reducing agent. Vitamin C, that's our primary reducing agent in our body. Vitamin C is water soluble. We also have vitamin E. Vitamin E is fat soluble. It's so we can store vitamin E. We can't store vitamin C. Vitamin A is an antioxidant, but it's mostly in our eyes. And the important part of that is in our eyes. Vitamin C, though, that's our primary. And how does it work? Like in the analogy, if you remember before, like how do I keep a bunch of hungry kids from eating plate full of vegetables. I mean, because if you're hungry, you'll eat those vegetables. Like, well, how do I prevent um, a room full of hungry kids eating vegetables? Like, well, if I put Halloween candy in front of the vegetables, the kids come and they eat all the Halloween candy, and then they get full and like, well, I don't need to eat the vegetables anymore. I'm no longer hungry. So how do you prevent a free radical from attacking your cell's DNA? Like, well, you put vitamin C there, and the free radical will attack the vitamin C. And once it's reacted, it's done. It's no longer hungry, as under the analogy there. It's no longer reactive. So in that regards, you need to constantly replace your antioxidants. Otherwise, it can cause damage. And that's where like the anti-aging and that kind of stuff. Well, anti-aging cream can be from ultraviolet light as well. So I should be careful what I say. So it's not just antioxidants. Although there is some people that suggest that overdosing in antioxidants may be a bad idea, but that's still being thought out. So hydrogen can be a reducing agent, and hydrogen can be dangerous because hydrogen can reduce iron to form iron hydride, and this is not a big deal for us in Hawaii, but places that it's cold, where you have a heating system, and if you turn on the heating system after letting it sit dormant for half a year, it can have iron hydride in there, and then heating it up can release the hydrogen gas, and then it can cause explosions. So how do we get around that? If you electrically ground your containers, so if you're wondering like why is my heater, if you live on the mainland or in Europe, or like why is my heater electrically grounded? Why do I have this connection to my outlet? What's going on here? It's because it's preventing corrosion that way. But it can also use it to reduce metals like tungsten. W is tungsten, and it's using hydrocarbons. So like if you want to go from alkanes and alkenes, we haven't talked about, that's the next chapter. Uh, so you can add hydrogen to that to change the molecules. And platinum or palladium is nickel too, I guess, can be used. Nickel isn't as good as platinum or palladium for this catalyst. Nickel is cheaper though. Platinum or palladium is typically used to do this. And what a catalyst is, it increases the rate of chemical reaction. It provides an alternate pathway, and it increases the reaction rate. Let's look more about hydrogen. So hydrogen is by far the most abundant element in the universe. Very, very abundant. It is relatively abundant on Earth as well. By mass, the Earth is mostly iron, and the crust of the Earth is mostly oxygen uh, by mass, but there's quite a bit of so most of the crust of the Earth is silicon dioxide, it's silicates. But there is a high amount of hydrogen, among other things, that's found in water. So, because the water is about 2/3 of the surface of the Earth. And we also use hydrogen to make ammonia and methanol. Ammonia we make in huge quantities, and this is because of fertilizer. And although the way we get hydrogen is usually by steam reformation of natural gas, so we get it from methane. And so hydrogenated vegetable oils, that's like margarine. So using hydrogen, use acids for that actually. So the way that you hydrogenate vegetable oils, you add vegetable oils and you add acid to it. So, okay. Also, uh, you can be prepared this way, but like I said, the way that we do it in industry is steam reformation. The other thing is by so oil refineries can make that if molecules are cyclized, hydrogen pops off, and it can be done that way. Then that's more of a byproduct fuel or byproduct than the actual um, uh, intentional making of hydrogen. Okay, where are we now? And living things. So uh, we get our primary energy source is glucose in our body, and we get the energy from it by oxidation. And but how is glucose made? It's made by reduction of carbon dioxide and 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 using sunlight as an energy. So photosynthesis, photo is light, light used to make things. I mean, of course, it does it in the chloroplast of the cell. Interesting. So I like it's really cool how the plants do this, and then of course this is where we get our oxygen from. And photosynthesis, the plant life has changed the atmosphere of the Earth. That 20% oxygen comes directly from plants. Of all of them, though, algae. People, of course, we have the picture of trees and grass here. Trees and grass are not the primary source of oxygen in the atmosphere. It's algae. Algae is where we get our oxygen from. At least the vast majority of it, on the order of 80% of it, is made by by uh, by algae. But okay, we are done for this one, and join us next time as we talk about organic chemistry.